In this video, we're going to go over the answers for Wednesday, April 1st. And we're talking about lipids and fatty acids in this section. And so the first thing we need to do is to be able to name our fatty acids in a systematic way. So the first thing we're going to look at is how to count fatty acids. And you always start from the carboxylic carbon, and you call that carbon number 1. And then you just count down the line. So this is carbon 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So you write down how many carbons you have, so 18. Then you write a colon to say how many double bonds you have. So we have 1. This delta tells you where the double bond starts at, so delta 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's an 18, 1, delta 9. For saturated and unsaturated, if you have any double bonds, you are unsaturated. Saturated means basically you have all the hydrogens that you could on your carbon. So if you have any double bonds, you're unsaturated. And for omega-3s, so there's actually two ways to number lipids. The carbonyl carbon is number 1, but the tail, you can say that's omega-1. And to count omega, you just start from the tail and work backwards. So this is omega-1, omega-2, omega-3, omega-4, omega-5. And if you're an omega-3 fatty acid, that means you have a double bond at the omega-3 position right here. So omega-1, omega-2, omega-3, you'd have a double bond right here. We don't, so we're not an omega-3 fatty acid. All right, moving on. So we have a 20 carbon lipid, 5 double bonds, delta 5, 8, 11, 14, 17. Unsaturated, this is an omega-3, so omega-1, omega-2, omega-3. Now we have an 18,3 delta 9, 12, 15 unsaturated omega-3 and an 18,2 delta 9, 12 unsaturated no omega-3. Question 2. So here's all of our tables for our fats. You don't have to memorize this, but let's look at some trends. So at the top we have saturated fatty acids, and the bottom we have unsaturated fatty acids. If you compare a 16.0 to a 16.1, the melting temperature goes way down. So 63 to minus 0.5. So it is easier to turn unsaturated fatty acids into liquid compared to saturated fatty acid. And to explain that, let me go back to this previous page. When you're all saturated, it's easy for your lipids to line up and have a lot of van der Waals interaction. So you form a nice solid. When you have double bonds, you get kinks in your tail. So it's straight here, but really it will be bent. And it's hard to line up these bent molecules. So you have much less van der Waals interaction. So you have a much lower melting temperature, as in it's easier to turn into liquid. Our next trend, as we look at our fatty acids, they always increase by 2 carbons, 12, 14, 16, 18, 16, 18, 20, 22, 24. So the carbons in our body, the common ones, the common biological fatty acids, are always units of 2. All right, more double bonds lower the temperature. So let's compare 18.1, 18.2, 18.3. Same number of carbons, different number of double bonds, and every time we add a double bond, we lower the melting temperature. Our double bonds are always spaced out by 3 carbons. So let's look at 18.3, 24, and 25, and you can do a 22.6 as well. All the double bonds are always 3 carbons away from each other. So we never have double bonds that are conjugated. If you remember that term from organic chemistry, it basically means a conjugate double bond means they're close enough to like interact, more or less. Here we're 3 carbons away, so these double bonds don't interact with each other. Also, our last trend, if we look at the no double bonds, the more the more carbons, the higher the melting temperature. And this goes back to my point I was talking about saturated fatty acids. If you're saturated, the longer the tail, the more van der Waals interactions you have along the tail, the harder it is to separate these fatty acids, the more like a solid it's going to be, and the more energy you have to put in to change that solid into a liquid. All right, question 3. This gets at your understanding of lipids. So bacteria can change their lipid composition of their membrane when grown at different temperatures. So we have 2 bacteria grown at 25 and 42. Which of the following differences is most likely to be observed? All right, so if you're growing at 25 compared to 42, at 42 you're hotter, so you want your lipids to have longer tails and you want to be saturated because you don't want your plasma membrane to turn completely to liquid. You don't want to melt. So you want your plasma membrane to be somewhat solid, not completely, somewhat solid. So if you compare the 25 to 42, the 25 will have lower levels of this 20-0 and 16-0, but it will have higher levels of, and it will have higher levels of 18-2 to 18. So the idea is if you're colder, you want your lipids to not be as saturated, because if all your lipids are saturated at cold temperatures, your membrane will turn to a solid, and you're trying to get a balance of your membrane where you're a little bit like a liquid but a little bit like a solid. So the colder you get, the shorter you're going to make your lipids because the melting temperature will decrease. Also, the more double bonds you'll have in your membrane lipids, again, because you're decreasing your melting temperature. You're trying to reach that balance of somewhat liquid, somewhat solid. At the 42 degrees, you're going to have a lot of 20-0, 16-0, 18-0. Well, you're going to have more 20-0 than 16-0. I guess that's kind of what it's showing here. So we're going to have more 20-0 at higher temperatures because we want our lipid membranes to be, again, that balance between liquid and solid. Right, so those were just lipid tails. Now we're going to talk about our tags, our triacylglycerols, which are 3 lipid tails onto this glycerol backbone. So tags are used for storage, not really in the bilayer. Why? Well, in the bilayer, you usually have charged head groups. These charged head groups will be on the outside of the membrane interacting with the water. Glycerol doesn't really have any charges. So CH2, 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 and you have this carbonyl group, but that's not really a polar head group like we want in our phospholipids. So no charge / polar head group. That's why tags are stored. So these are energy molecules. All right, so now we're going to get into glycerol phospholipids, which are a special class of lipid that has this head structure where you have fatty acid tail, phosphate now, and this X represents any possible head group shown in this table. So which head group can form hydrogen bonds? So everything except an ethylamine, a choline. And the reason is that you'll have an OH here, so that can form a hydrogen bond. NH3 plus form a hydrogen bond. Here, our nitrogen has 4 things bonded to it. So even though it's positively charged, it doesn't have any space to hydrogen bond. Remember, carbons and hydrogen, a hydrogen bound to a carbon can't be in a hydrogen bond. It's not polar enough. So your hydrogen has to be attached to a nitrogen, an oxygen, or a fluorine. Choline, that is not the case, so it cannot hydrogen bond. Serine, myoinositol, glycerol, and phosphatidylglycerol all have oxygens or OHs that you can hydrogen bond, just not choline. So autoimmune diseases can recognize DNA can sometimes also recognize phospholipids. What are they binding to? So the question is, what is the same in DNA as in phospholipids? That's the phosphate. So remember, this phosphate group is in DNA and RNA. It's also in your glycerol phospholipid. Right, so we're getting to another class of lipids, which are sphingosines. Sphingosines, the head group is shown here. And you can have a ceramide, which is you take your sphingosine, you add this carboxyl or carbonyl group to this NH3. This R is a fatty acid tail. But this is the head group for all sphingosines. This is the head group for ceramide. And sphingomyelins are a type of sphingophospholipid. So it gets very confusing. But you have your sphingosine part right here. You have your phosphocholene, so that's why it's sphingophospholipid, and then you have your fatty acid tail on the nitrogen like we saw. So I have a bunch of questions to try and get at your understanding or see if you understand these different types of lipids. So which of the following are true concerning sphingophospholipid? So sphingophospholipid have a sphingosine, so that's the head group, and they're also a receptor component. So our sphingolipids are usually going to be in your membrane, and they're also going to be a receptor for your membrane. Question 7. Glycosphingolipids have several attached carbohydrates and at least one celiac acid. What are they called? Those are called gangliosides. So what I'm getting at this question is I would like you to know like the basic head groups for gangliosides, cerebosides, and sphingomyelids. Basically, if I was to give you a head group, could you say am I looking at a sphingomyelin? Am I looking at a cerebroside, or am I looking at a ganglioside? Question 8. Where do we attach a fatty acid for a ceramide? So based on our previous picture, our fatty acid goes for this NH2. That's the only place we're going to put the fatty acid for the ceramide, so that's A. That ends all our material for test 3. If you have any questions, as always, please email me and I'll answer them as soon as I can. Otherwise, I'll see you in the next video.